Okay, so we now have proportional control right here, where we multiply our error by this proportional portion. Now we're going to go ahead and add in derivative control, our integral control, and derivative control. So let's start with integral. And so this integral component we're going to calculate, and then we're going to add it to our total right here. Okay? And so we'll go ahead and up here, we're going to create const float ki. And we're going to set it to 0 for now, but we can update that later. Alright, now let's come down to here. Okay, so the way we're going to calculate this is we're going to multiply the error by our ki term, and then we have to multiply that by the amount of time that has passed. Okay, and so let's come to here, and we'll say unsigned long current time equals millis. And then what we'll have to do is we're going to need the previous time too. So we're going to say unsigned long t is equal to prev time minus current time. So we'll make a global variable called put down here. So unsigned long prev time. Okay, and so we're going to subtract those, and that's going to be the time. And then what we're going to do here is we're going to set the previous time to be equal to the current time. Alright, and so every time through the loop, we'll figure out how much time has passed, and then update the previous time there. Okay, and so we do that, and then we have to add that back into the previous I. So let's see. What we'll do is this. We're going to make I be a global. Okay, and so then when we calculate I, so the integral term is accumulating error, so we multiply our error term by our error constant, our integral constant, and we multiply that by the amount of time that's passed. And so that basically represents the amount of error during that time period, and then we add that into our existing error. Okay, and there we have our integral term, I apologize. And now let's add in our derivative term. And there's some things that we can do that we'll come back and do later to kind of limit the impact, and so there's some issues that can occur, such as like integral windup, where we basically oversaturate the device and things like that. And so let's see, we want to do floats d. This is going to be equal to the error times no, this is going to be equal to the this is actually equal to the velocity of it. So we want to we're going to multiply KD, we're going to divide it by the time, by t. Let's actually convert this to a float here. We probably should do that here too. And then we're going to multiply this by the change in position. So our current position, current value, minus our, I think it should actually be the previous value minus the current, we'll just go like this, minus the previous value. value. Okay, so what this does is it's going to calculate the derivative component by taking our derivative constant, dividing it by the amount of time that's passed, and then multiplying it by the change in position. So this is basically taking the velocity and velocity is the displacement, and then over dt, change in position and change in time, and then we're multiplying that by that constant. Okay, and then we'll put a semicolon here, and then what's going on in this one is for I we're taking the error and we're multiplying it by the constant. Well, this is integrating. I can't even put the symbols on here, but it's basically it's essentially taking the error for every instant and adding all those errors up, and scaling them by the interval constant here. Okay, and then just for consistency, let's actually pull out our derivative, our proportional term too. And we'll put the P right here. Okay, and so that's the basics of our PID controller. We've got to come back here and add in our derivative term too. Oh, you know what? We're not done yet because we didn't finish this part. So we got to the previous value. So after we do this, we're going to set the previous value equals current value like that, and so it's going to update that, so every time through the loop is referencing that previous value. Okay, now I'm going to change that. Instead of current value, let's do current position, and so every time we reference that we got to update it. Current position, we'll calculate our error with it. Okay, I think that's all of them. And then, so we got the previous value. Let's make that variable here. Float prev. We'll call this previous position. Okay, and then let's come to here. Make that to be previous position. Alright, and I think we have the basics of our PID controller. Okay, so next steps will be to go back and we can work on getting these constants figured out, and we'll talk about figuring out those constants. But once we have those figured out, what we might find is we want to do some things like, for example, so we don't end up with a really large amount of error accumulated, we might do some modifications here so we don't max out, or so there's like a cap to this integral term, or that it could time out or something. We may want to do some filtering with the derivative term, so if there's like a weird bug where we get a bad measurement or something, it doesn't like freak out. And then yeah, but this is the basics of it. We'll also kind of implement this as a class as well.